That's my fault. They're going under time. Mark is promising he goes under time. And then after this is there another. Who has the schedule? So you're before lunch. Yes. Excellent. We have a great session. I have no idea. I just show up and it was a great session. Somebody wasn't me. But we have two of my favorite optimizers back to back. First, Mark Schmidt is going to talk to us about actually making block coordinate descent go fast. Hopefully. Okay, good. There we go.
All right. So after all the talks, okay, can everybody hear me?
Yes.
All right. So after all the talks yesterday, I was thinking of doing this and joining the trend and talking about something more theoretical. But Ben said it's okay to talk about practical stuff. So we're not going to do that. Yesterday, maybe not today. Okay. So block coordinate descent is pretty widely used for large-scale optimization. Really easy to implement. Not big memory requirements. You don't need infinite RAM. There's cheap iteration costs, and it can be used in distributed setting. It's been used for almost 2 decades for lasso and SVM problems, which are kind of two of the canonical optimization problems in machine learning. And so if we can improve on this method, we could probably affect a lot of applications. So this work is basically a grab bag of different ways to try and make existing BCD methods go faster. There's no unifying theme, but hopefully you'll see one of them that's at least interesting for your problem. So my notation, we're minimizing a function f of x in r to the n. We're going to say that f is differentiable and n is large for most of the talk. We'll talk a little bit about non-smooth problems near the end. Each iteration of BCD, you select a block bk, and it's going to be a subset of 1 to n. And then you take an update. And we use this notation ubk to basically grab columns of the identity matrix. That means this dk is going to be the size of bk, and we just update the coordinates associated with bk. And we choose this dk usually so that it improves on the subproblem if I just focus on the subspace associated with the blocks I chose. So for example, I might just take the gradient of the blocks that I chose and take a negative times a step size, so I do like a gradient descent step on that block. So whenever you talk about coordinate descent, you always have to include this slide, even though many people do not. So coordinate descent is actually a provably bad algorithm in general. It's actually slower than gradient descent in terms of the convergence rate, and the iteration cost in the worst case is actually basically the same as gradient descent. So if you have, okay, so we'll come back to that. But it's actually widely used in practice. So for certain problems, nothing seems to work better. So maybe not the most effective for fitting MNIST, but for a lot of problems in statistics, they really like this algorithm. Coordinate descent is also used in graphical models and a bunch of other settings, and it's quite hard to beat in some of these settings. So if you haven't seen this before, this seems kind of weird that we've got this algorithm that lots of people use and has terrible theoretical properties. So we've recently understood coordinate descent a little bit better. And this sort of started with a work of Nesterov, and there's been tons of papers on this lately, who analyze randomized coordinate descent. So I pick a random coordinate or a random block of coordinates, and then I do a gradient descent step on that. And one of the conclusions, which isn't spelled out explicitly, but it is implied by this work, is if I can make my coordinate descent iterations n times cheaper than my gradient descent iterations, then I might be better off doing coordinate descent. It turns out that in these fields where they use coordinate descent a lot, this was actually true. So we need to talk about, if you're going to apply coordinate descent, we need a class of problems where it actually makes sense to apply coordinate descent, because otherwise you shouldn't do it. And here's the class of problems that I like to talk about. So we're going to minimize a function, let's say g of x. G of x can have a separable term. It can have what I call a pairwise separable term, so a set of functions that depend on pairs of variables, and this composition of a smooth function with a matrix a times x. So why is that sort of class special? Well, if I have the separable functions, updating one of those functions is n times faster than updating all of them, so that's nice. This one's a bit weird, but if you think about updating one xi, I change n terms in that sum, whereas there's n squared terms in that sum, so I can do it n times faster. And then this one is also a little bit weird, but the key idea here is if you track ax, you can actually do the updates in O of 1 instead of O of n when you have n variables. So when you're talking about coordinate descent, you're pretty much only talking about problems that can be put in this form. Now, this seems like a really restricted class, but it includes a lot of functions. So most of the models in machine learning fit in this framework. So if we have like an least squares term and an L1 regularizer, I've got my separable term and I've got my f of ax. If I have a quadratic function, in the last talk, I've got my separable term and I've got my pairwise separable term. So there's actually tons of objective functions that show up in machine learning that have this structure, and that's one of the reasons it's become so popular in machine learning. If I let you update blocks of variables instead of one at a time, it opens up some new problems like group L1 regularization, where you have some sort of group separable versions of the problems on the last slide. If people know of other problems where you can apply coordinate descent, please email me. I always ask this and nobody ever does. So coordinate descent might just be for problems that can be written in this way. Maybe Ben will come up with one at the end of the talk.
That's good. What do you need more than that?
Well, many people want more than that. But for this talk, we're only going to talk about those problems. OK. So our usual assumption when we analyze coordinate descent is we say we're LB blockwise Lipschitz continuous. So if I change the coordinates b by some value d, we're less than L times the norm of that d. And if you have a twice differentiable function, it's just saying that if I grab the b by b submatrix of the Hessian, its eigenvalues are bounded above by L. There's lots of ways to pick the blocks, and there's lots of ways to pick the directions. So here's a canonical randomized BCD method, which I think was the one used in the last talk. Maybe Ben can verify that. So I partition the coordinates into blocks. So just 1 to tau, tau plus 1 up to 2 tau, and so on. Then I choose a block uniformly at random. And then I do my gradient descent step with a step size of 1 over L for the block. Is that the previous talk algorithm?
Well, except for in the quadratic case, you can do a full step. So
OK, so here you use a line search, which works much better. OK, if you implement this algorithm,
then an exact step?
pardon?
You can do the exact. You can do an exact line search. So the only difference.
Actually, in the quadratic single coordinate case, 1 over LB is the exact step.
Oh, that's true.
Yeah.
That's true.
So
with the blocks, then hold on. So now I'm confused.
not with blocks, yeah.
Yeah, with blocks, you can also do the exact line search.
Yeah, that's right. OK, so you see this algorithm in a lot of papers. If you implement it and try it out, and you generate your least squares problem from like random Gaussian data, it works great. If you apply it to a real problem, this actually often works pretty badly. And we saw that in the last talk. OK, so let's think about this. We can make a blockwise version of the descent lemma. So we can bound how much f of xk plus 1 is going to be lower than f of xk in terms of the gradient and how much we move and this value L. If I plug in that step from the last slide, I get this progress bound, which is saying that how much I improve the objective depends on the norm of the block and the Lipschitz constant of the block. If I now take the expectation of that with respect to the block, I can get sort of a bound on how much progress I make with random sampling. But for certain problems, you can do a little bit better than uniform sampling. So I'll show the structures on the next slide, but two things you can do. One is Lipschitz sampling. We actually choose the block proportional to its Lipschitz constant. So if the Lipschitz constant is big, we're going to sample that block more often because we expect the gradients to be changing quite quickly. Another thing you could do is called Gauss-Southwell, where we choose the block maximizing the norm here. So if you look at this bound, if I make this norm as big as possible, then I can, in some sense, expect the most progress if all the Lipschitz constants are similar. Now, when you first see this, this looks really strange. How can I compute the max of the gradient n times cheaper than the gradient? OK, so let's think of a problem with a very sparse Hessian. 10 non-zeros per column. And I have the gradient from the last iteration. When I update one coordinate, I'm only going to change 10 gradient values. So instead of recomputing the gradient from scratch at each time, what I do is I track the gradient. And if not many values are changing, then I can actually maintain the max the whole time by just using a max heap to keep track of where the max is at all times. It actually works not just for sparse problems. If you have a dense quadratic problem, as in the last talk, it also works. It ends up being that Gauss-Southwell basically has the same cost as randomized, at least in O notation. The condition you actually need is that the max degree of the Hessian, if I view the Hessian as an adjacency matrix, needs to be similar to the average degree. So that's great for super sparse graphs. It's great for dense graphs. What you cannot have is star graphs. You can't have one node that's connected to everybody. We don't want hubs or things like that. If you don't have that, there was some work recently talking about how to approximate the Gauss-Southwell with a nearest neighbor search problem for certain linear models. So that's kind of neat. Now, yep.
Sort of maybe it's a meta question of why are we using a step size as opposed to a Newton step?
We'll get there in like 3 slides.
Okay.
Yeah, we definitely don't want to use the gradient step. Okay, so instead of choosing the block that maximizes the norm here, we really have this LBK in our bound, so we should use that too. So we call that the Gauss-Southwell-Lipschitz rule. If you incorporate the gradient norms and the Lipschitz constant, basically has the same runtime as using Gauss-Southwell, but it's a bit faster. The intuition here is if I have 2 coordinates and they have almost the exact same gradient, I should choose the one whose gradient is changing more slowly. Because if I take a step along that direction, the gradient is going to sort of stay big as I go along that direction, and so I can expect to make more progress. Another thing to talk about is when you're in the block case, this issue of fixed blocks versus variable blocks. So for a lot of problems, we just partition the coordinates into a set of blocks of roughly equal size, and then we just pick one of those blocks. But one alternative you could do is just consider all possible blocks up to some size tau. So if you consider all possible blocks, you can clearly find one that has a bigger norm, or norm divided by square root of LB, than if you consider these fixed blocks. So if you can afford it, you should use the variable blocks case. But for some problems, variable blocks doesn't make sense. So if you do sparse multi-class logistic regression, it ends up variable blocks is much more expensive. If you have a group separable problem like group L1, you can't actually do variable blocks because they don't respect the non-smooth structure. And something that was kind of weird is that rule from the previous slide where you divide the norm by the Lipschitz constant ends up being NP hard if you want to have arbitrary blocks. So that's sort of associated with using fixed blocks, which was a bit surprising to us. So I'm going to actually show plots in this talk. Here's all of our randomized and cyclic methods. On the left is a binary logistic problem. On the right is a multi-class logistic problem. And in coordinate descent papers, you see a lot of this problem, but you don't ever see this problem. And coordinate descent methods look pretty bad in that case. And this is MNIST, but I'm just using multi-class instead of binary, or instead of least squares. So here's all the greedy methods, and they can make quite a bit of progress. So the difference between adding the difference between being greedy and using random or cyclic is pretty large. And then going to the Lipschitz constant helps a bit, and going to variable blocks can also help quite a bit. And we did lots of plots, so my students have been trying to figure out what really works. These differences get smaller as the batch size gets bigger. So the more things you're updating at once, the less it matters what rule you use. All methods work better if you do a line search or if you have the optimal step size. And we also found that if I sorted the Lipschitz constants and partitioned based on that, it worked a lot better. And this kind of goes against what the theory says. The theory says we should have blocks that have similar Lipschitz constants, but it actually ended up being working better if you put all the big ones into one block and update them all at once. And I think the reason for that is that if you can make the gradient of those close to 0, then you're forced to pick a block that has smaller Lipschitz constants on many of the iterations, at least half of the iterations. So that was kind of something that the theory hasn't caught up to yet. Okay, now our ideal rule is what's called the maximum improvement. I try every possible block of coordinates, and I choose the one that maximally decreases f. Now, if I have a quadratic function and I'm using block size of 1, that rule from the previous slide, that's actually the maximum improvement rule. So if you have a quadratic function, you have to change one function to save your life, you should choose this GSL rule. If you have block size bigger than 1, then you don't want to use that rule. There's better rules possible. And as was just asked, should we really be doing gradient steps anyways when we have blocks? So heading towards a Newton step, instead of defining Lipschitz constant based on a scalar, we can use a matrix HB. So here I'm using quadratic norms, and I'm assuming you're one Lipschitz in some quadratic norm HB. Not actually a stronger assumption, just changes how we measure. So one implies the other. Our descent lemma now just adds the Hessian here, or the Hessian upper bound here. And our update basically ends up being something like a Newton step, except for instead of the exact Hessian here, I have this matrix upper bound on the Hessian. Okay, so if I do that, I can actually consider updates that take into account that matrix when they're trying to choose the coordinate. So instead of choosing the one with the biggest norm or the biggest norm divided by L, I can choose the one that has the biggest norm measured in its Hessian, which I'm calling Gauss-Southwell-Quadratic. And this is nice because if you actually are a quadratic, it's choosing the optimal block. Something annoying is I now need these matrices, and this could be very expensive. So the alternative that many people come up with in this case is to use a diagonal approximation. And we just make this H a diagonal matrix. So once I've picked the block, I still do the Newton-style step. I don't do a diagonally scaled steepest descent step. But to pick the block, to do it quickly, I use the diagonal scaling. And a weird thing is if you make these diagonals only depend on the particular coordinate you pick, it's actually not NP-hard anymore. So that's kind of a nice thing. Is we went to something that seemed more expensive, we made an approximation to it, and that made the NP hardness go away. Now this is just as hard as the regular Gauss-Southwell rule. We also played around with iterative hard thresholding and OMP to try and solve this. Those I'll show the plots, but they didn't make a huge difference. So these are our plots. Here's if you use fixed blocks, and here's when you use the variable blocks. So when you're using the variable blocks, and now we're doing the Newton-style update, the variable blocks actually help a lot more than they did when you had these fixed partitions. So that was kind of interesting. When you're doing fixed blocks, there seems to be no point in incorporating second-order information into the block you choose. It didn't really help at all. And then when you were doing variable blocks, it did seem to help, but the diagonal seemed to basically have all the work done for you. So there wasn't any reason to use more expensive matrix updates or stuff like that. So the good news here is that these sort of better rules have the same cost as the classic rule from 1940. So that's nice.
Did you play with block size?
We did play with the block size. So I'm just cherry picking some results, but in our paper we have like a 15 plot table that has all sorts of block sizes and variations and stuff like that. So something that was weird for the Newton methods is the difference between these methods actually got larger for larger batches up to a certain point. So when you were doing Newton updates, having big blocks and a good rule actually made a big difference. Whereas for the gradient methods, you just want the blocks small. It seemed like big blocks didn't help much. Okay, so this was our update using a matrix now. And it's not quite Newton's method. So Newton's method, we would have the instantaneous Hessian, and we would have a step size here. And some people are calling this a Newton block coordinate descent, but I think that's not the right name for it. Because if you consider an xk, where the Hessian is actually much smaller than its upper bound, then the Newton update can actually make much more progress than this upper bound update. Or if you took a code implementing Newton's method for all the coordinates at once, and you replaced it by a fixed Hessian, you've just thrown superlinear convergence out the window, unless you happen to pick the Hessian at the minimizer, which you probably won't do. So I think, even though people are calling this Newton method, we're calling this just matrix update to distinguish those things.
Quasi-Newton?
I'm not calling it quasi-Newton. It doesn't satisfy any quasi. If you don't satisfy quasi-Newton equations, we're not calling you quasi-Newton.
Secant equation is not quasi-Newton.
Yes.
Right.
Do you agree? Great. Okay. Quasi-Newton's thrown around way too much. Okay. So now the disadvantage of Newton is now we need to a line search or a trust region. So if you want it to be really simple, you have to put in a bit of extra effort. You have to tune some parameters, and you have to evaluate the function a few more times. So we thought maybe instead of doing Newton, we can do this cubic regularization of Newton stuff introduced by Polyak and Nesterov. So instead of using the descent lemma, we actually go to our third order term here, and we assume that the Hessian is Lipschitz continuous. And then we have this bound TBK on the sort of continuity of the Hessian. So this would be nice, at least in theory, because I could guarantee the decrease without having a line search or any extra function evaluations. I could have negative curvature in my Hessian, which is usually not allowed in line search methods, but that's very nice for non-convex problems. And the only problem is it seems like it's NP hard to actually compute these TB values. And I've been spamming a lot of tensor people, and if people in the room know the computational complexity of computing this for like a logistic regression problem, I would be very happy to talk. But if your block sizes are small, you can actually just compute these numerically. So for block size of 1 for logistic regression, there's just an analytic formula. It's like 1/6 times square root of 3 times like the 3 norm of the largest example or something like that. It's just application of quadratic formula. And then for you know, if the block sizes are small, we can solve NP hard problems. So that's nice. Just an example of what the difference is. I don't have the matrix update on this plot because I've been making my students do too many experiments. But here's gradient updates. This is Newton, where we've taken into account the cost of line search. And if you don't take into account the cost of line search, the Newton and cubic method are right on top of each other. So at least for this problem, the cubic sort of gained you some time. So now that we're talking about Newton methods, you should be thinking superlinear convergence. And so you might ask, does BCD have superlinear convergence? And the answer is definitely not. So if I give you a 2-variable quadratic function and the off-diagonal is non-zero, you can apply coordinate descent, but it's not going to get superlinear convergence, even though you can compute the exact update. But there are some problems where you can actually get superlinear convergence with BCD, and that's the next thing I want to mention. So let's say we have a smooth f and then a separable non-smooth g. So imagining g is an indicator function that the x's are positive or that they're less than some upper bound. Or it could be like an L1 regularizer, so we want to get a sparse solution. In this context, we usually use what's called the proximal gradient step. So we take a gradient step with respect to the smooth part, and then we compute what's called the proximal step with respect to the non-smooth part. And many of the issues are exactly the same in this setting. So you get roughly the same convergence rate as if you didn't have the non-smooth term. You can talk about variable blocks versus fixed blocks, gradient versus Newton, random versus greedy, and so on. So I don't want to talk about that. What I want to mention is some of the differences. So one thing is I had some arguments with my student because we all thought the Gauss-Southwell rule was a different thing. It turns out there's 3 different Gauss-Southwell rules in the literature for this problem. Only one has the nice theoretical properties. So you want to look up something called the GSQ rule if you're interested in that. And the non-smoothness can actually lead you to a faster convergence rate. So normally we think of proximal gradient as leading to a convergence rate that's the same as if we had a smooth problem. But I want to argue that if we have a non-smooth problem, proximal gradient might actually converge faster than if we just had the smooth problem. So let's think about the simplest case possible. Minimizing f of x, and I want all values of x to be greater than or equal to 0. So just optimization with non-negative constraints. In this case, my proximal gradient is I take my gradient step and then I project it so that all the elements are non-negative. So I just set negative elements to 0. And that often gives us a sparse solution. So this is used in non-negative matrix factorization, non-negative tensor factorization. This has some sort of sparsity in the solution x star. And what I want to emphasize here is what's called the manifold identification property. Is that if I take all k larger than some k prime, the sparsity pattern of my xk is going to be the same as the sparsity pattern of the optimal x star. So if you're ultimately interested in what the final set of non-zeros are, you don't have to run the algorithm forever. After some finite number of iterations, you know what the final non-zeros are. And this is nice, because actually once you're at the final set of non-zeros, you're effectively solving a lower dimensional problem. Instead of solving the problem in the original n-dimensional space, you're solving the problem in this lower dimensional space, and so your condition number should be better in the lower dimensional space. So if you want to prove that that happens, the usual assumption for non-negative constraints is that the gradients at the solution for the values that should be 0 are strictly positive. They have to be bigger than 0. So if the gradient of the solution is 0, then you have a problem that you can approach the solution from the interior. But as long as the gradient's bigger than 0, you can actually have this property. So this has been proved for BCD methods by Stephen Wright in a very nice note. And we gave sort of an alternative proof that's maybe a little bit shorter. But more importantly, we also look at how many iterations does it take before you find the final sparsity pattern. So there's many, many papers that say you eventually identify the sparsity pattern. But since we're doing computer science here, we really want like not an asymptotic result. We want to bound on saying, if you run it for this long, you find the final sparsity pattern. So if you run projected gradient and you do condition number times log of 2L starting point divided by zeta, this term here, you will have the final set of non-zeros. And so that's kind of nice. So at that point in time, you know your algorithm is actually going to be converging faster based on the final support. Now, this looks a lot like the convergence rate of gradient descent. And it's very similar, except for instead of epsilon, we have this zeta here. And so if your gradients at the solution are quite positive, then you actually identify the non-zero pattern very quickly. And if they're very close to zero, it might take you a long time before you identify the non-zero pattern. We also gave the bound for BCD methods. It's slightly more complicated because you have to take into account how long it takes before you pick all the coordinates that are supposed to be zero, but it's basically the same idea. And we did the same thing for like L1 and the general case. So in the general case, you have to have this condition that the gradient is in the interior of the subdifferentiable of the non-smooth part. But basically, we can get bounds on how long, if you're solving L1 regularized least squares, how long it takes before you identify the final sparsity pattern. And I haven't seen things like that before, so that's nice. And it's very simple. Yeah?
What would the analog be for non-collisional if not L1, right? Group lasso, like nuclear norm?
Nuclear norm, I don't know. Group lasso, we talk about in the paper. What you need is you would need the norm of the group that's supposed to be zero to be strictly less than, the gradient to be strictly less than lambda.
And zeta is how much strictly less it is?
Yeah, zeta is like the gap. Okay, so if you have this manifold property, so this was known for a long time, you can say, I'll run BCD for a fixed number of iterations to identify the final sparsity pattern. And then I'll just run Newton method or quasi-Newton on the non-zero variables and get my superlinear convergence. That's fine, but even though we know it's bounded, we don't really know how many iterations to run this for. So I prefer hybrid strategies. So one is you try the BCD and the Newton step on the manifold at each step and take the best. And this was from Stephen Wright's paper. Another thing you could do is you could just do the Proximal-Newton version of block coordinate descent, which is not too expensive if the blocks are small. And if you have a piecewise linear GI, you can use homotopy methods to actually compute that pretty quickly. There's also something called two-metric projection methods, which is some sort of nice compromise between cost and progress of the iterations. If you use the hybrid method, you can actually get your superlinear convergence, which is nice. If you use these other two methods, you can get it if you use a greedy rule and you have sufficiently large variable blocks. So it's actually possible for BCD methods to get superlinear convergence in some of these settings because they eventually identify the final set of non-zero solutions, and then they effectively apply Newton on those steps, which turns it into a Newton method. Okay. For quadratic F, I should also mention that when you find the final set of non-zero things, you're actually done. So if you're solving lasso or you're solving SVM problems and you use an approach like this, eventually you find the right set of non-zero variables, you solve it, and then you have an exact solve for your SVM or lasso problem. So you don't even have an epsilon anymore. You're just using direct solve, which is nice. Okay, so last thing I want to mention is, given that lasso and SVM you can do exact updates, are there other problems where we can do exact updates? And one case is quadratics, but there we need a tau cubed, so we can't have our blocks be too big. Another case, which was talked about yesterday by Levin, is if we have sort of sparse quadratics, then we can do this sort of zero fill-in Cholesky factorization and do it quickly. So this has been sort of used for a long time in iterative solvers. So if you read like Demel's book or something like that, they'll talk about red-black ordering, where if I have my structure being a lattice dependency, I update the red nodes, and then I update the black nodes. And since they're not neighbors of each other, there's no dependency. I just get a diagonal quadratic system that's easy to solve. But with the ideas from like graphical models and chordal graphs and all that, you can instead use things like trees. So if I grab a tree-structured subgraph, I can exactly compute the Newton step or do the exact block update if it's a quadratic, using message passing algorithms, or which is, in this case, is equivalent to a Cholesky factorization, but with no fill-in, so it's linear time instead of cubic time. Okay, and that makes a big difference too. So if you just sort of pick generic blocks, you don't do too well. If you update trees, you do quite well. And then the red-black ordering is usually somewhere in between if you have a special problem where you can use the classic red-black method. So to wrap up, because my voice is not going to last too much longer, sometimes you can really afford to do greedy BCD methods, and in those cases, you probably should. So in those cases, we propose some rules that make them go slightly faster, and they sort of can even incorporate second-order information in an efficient way. But if you can afford to do second-order information, you probably should. Cubic regularization might be a way to avoid a line search if NP-hard problems don't scare you when they're small. You can do message passing to very efficiently compute those updates when you're very sparse. And two-metric projection methods are a nice way to handle non-smooth cases. And then from the theory side, the most interesting thing was we gave bounds on the number of iterations to reach manifold. So the number of iterations, you run an L1 solver before it has the final sparsity pattern, which might be useful in other settings. I can imagine that also leading to new algorithms where you take advantage of some property like that. Okay, I'm going to end early because, as you may guess, my voice is bad. I will just finally mention that this was almost exclusively work done by my two students and over a while, but I've sort of bugged them to rewrite it and make it right. So the paper will eventually be up. I'm just the bottleneck in making it happen. Yeah, thanks for listening. Yep.
So sparse inverse covariance selection, does it fit into your form that you started?
The answer is I have no idea.
Because you can do coordinate descent with exact steps.
Yeah.
On that.
And what is the cost of the exact steps?
So it's.
I'm hoping it's n cubed over n or something like that.
Right. So it's n square, right?
Yeah. So in that case, it would fit.
Right. Okay. But in the beginning you showed the form of sum of fi's, right? Plus.
Yeah. So the log determinant must have some special structure that lets you do that. So maybe I do have to update my list.
Yeah. I wonder. And I mean, it doesn't work very well, but maybe there is a way to improve it.
Yeah. I mean I'm still not completely sold on block coordinate descent. It's not my favorite algorithm, but we at least got it working way better than what people are using right now. So.
Right. And there, it's also for sparse inverse covariance. It's also very parallelizable.
Yeah. So I didn't talk about parallelization at all, but in general, the BCD methods are pretty amenable to parallelization. The only problem is choosing the step size when you're doing stuff in parallel.
But I don't mean even that. I mean, every iteration is like, you can distribute the matrix, because you have matrices, right, to deal with, you can distribute it. So.
Is there a question in the back?
Why do you need like a two-phase analysis? Because even though you're not in a lower dimensional subspace, but you are still kind of in a lower dimensional tangent cone or something, right? Like your iterations are still in like a restricted space.
My iterations are still in a restricted space, I agree, but I don't know which space they're in. So we didn't actually do the full analysis. We just proved how long it takes to get to the manifold. We didn't try and prove the total time of the entire process. So that would be a great something for someone in this room to do, is sort of prove that the whole procedure benefits from this manifold identification. Yeah.
So, about the manifold identification. It seems to me that you need to know what's the optimal in order to verify whether that property is true. Is there any class of problems in which you can say even before, knowing the optimum if that condition is verified?
Yeah, great question. So it seems like I need to know what the optimal sparsity pattern is in order to say anything. So all we did is prove bounds on the number of iterations before we know it's correct. So in that sense, I don't need to know. But there is work trying to identify what the optimal sparsity pattern would be early, and that's things like safe screening rules. There's a big literature on that, where you try and identify it early or try and rule out variables that can't be part of the solution.
Yeah, just to that point, I have a paper from about 10 years ago with Christina Oberlin, which in the setting of nonlinear programming, where it does reliable identification of the inequality constraints.
Okay.
So it's based on having it bound to optimality in conjunction with some measure of how inactive they are. And so it's sort of asymptotically guaranteed to get the right answer.
Just to follow up on that, that is a very nice paper, and I did not mention a lot of references because I made the talk last night. But we have about 80 references in the paper. BCD is a very well explored space, and we tried to be very thorough in sort of characterizing all the things that have come before. So when the paper's up, which will hopefully be soon, there will be a lot of these things in there.
So presumably, if you assume some statistical assumption, like for example, if you do lasso, you should be able to estimate at least what is the dependence of the constant zeta on the amount of data you have. Are there statements like that?
Oh, great question. Okay, so the question is, if I make some sort of like statistical assumptions on the data, maybe I can bound zeta. I would love to see that. Not, off the top of my head, I have no idea how to do that, but I'm not a statistician, but that would be really neat if you could do that.
But empirically, do you see like do you have an indication of how these things, like the time to identify, depends on the, like let's say the number of measurements? They're just hard to figure that out.
We haven't done any experiments trying to characterize that. I know that it happens way faster than you expect. So there has to be some sort of explanation for why it happens so quickly. Yep.
So you mentioned for some of the problems that, especially when you have few blocks or when your blocks get really large, that this grouping by the smoothness parameter actually helps. So I'm wondering if that actually is so in a very special case when you only have two blocks, there are results that say that you are actually paying the minimum of the you're paying the for your running time is the minimum of optimizing like the two subproblems. But the catch is that you would be you need to solve them optimally. Now I suspect that this could be generalized to like any constant number of blocks. But again, the catch is whether you're solving things, like whether you're just doing a gradient step or some other step, or if you're really doing a line search and doing like just minimizing really well over blocks.
Yeah. So. I don't completely follow the minimum thing. Maybe we can talk about that afterwards. But so related to this is I had a guy come to me and say he wants to do a postdoc with me. And when you're from my school, I usually say, okay, let's work on a project for 3 weeks. And I gave him a project similar to that, saying like, you know, is that really the optimal rule if I'm going to do a sequence of steps? And he came back 2 weeks later with a whole bunch of math and saying, no, it's not optimal. There are better ways to do. So I think I will give him a postdoc.
But were the problems you were considering, were they such that your individual steps over blocks were really, really good? Or not? So that's sort of the...
Yeah, so my thought is you should always take the best step on the block possible. So the very first experiment I showed, we were doing gradient steps, but I wouldn't advise doing that at all. You should do like the Newton step or something more fancy. You can, like, especially if the blocks are small, you can always afford to do something more fancy than the basic step.
That was a great question and answer period. I want the last question.
Sure.
If you don't like coordinate descent, what are you going to advocate for? Think about it. Tell me over lunch. Say more. That's a trick question.
The two things that I use are LBFGS and SAG right now.
Oh, well, there we go. All right. You had an answer. All right. Let's thank Mark again for a great talk.